Now let's go to the perspective projection and get an understanding of what this is about. To go from the night to day, or from linearity of the night to the circularity of the day. And in Corbusier, this is about the sunrise, going out of your house, of the production, of the dreams of the night, and enter the bright sunlight out there in a new notion of space, which is not encapsulated in the speciality of your home. So, the perspective projection. So we want to start with the gnomon. This is his vertical stick. This Apollo and the moon, and this, or with Thales, ancient Greek mathematician, and the pyramid. We put this stick to the ground vertically. There's a sun. There's this line. We have the shadow meets at the ground. So as the sun moves, the shadow goes. So therefore, this is a clock. This is time. This is a clock. But this gnomon is also a GPS. And this is how it works. So if you look at the movement of time and the shadows, you see this here, this curve here is an hyperbolic. And the hyperbola is if you cut a cone. A cone again is an axis of linearity combined with a circularity. So this is space and this is time. So if you cut that with a plane, then the area of cutting is a hyperbola. So this is what we see on the ground. So now what is characteristic for this location is an area. So we see this area, and the area is defined by this. If this is the point here, this area is specific to this location. This is constant. So if we go here, like with all hyperbolas, if we go here, and this is the same area, whatever it is. So, and that's the GPS of the gnomon. And what we talk about is the preservation the covering area. That's the interesting thing. So this gives you the circularity of time at each point in a specific way. And by that, you get a notion of a new space, which is not this line, a certain line, not the curve of time, not this line you can see, but the principal conception of an area in the point. So that's what the perspective projection is. So it's very abstract. In physics today, it's called objective chance. And this is the thing you can get from time, from the dreams of the night. From time, you're able to project to space. So, go one step further. So, it's very abstract. To give you that you trust in the things. Go for Pythagoras. If we have A, B, C, if this is a right angle, we know A squared plus B squared equals C squared. So, what this is about, getting point A, point B, point C, and get them in a certain constellation in a notion of space we don't know. So this is when we leave our comfy home in the morning and enter so everything we know, it's completely transparent what we know, and enter a world which is a new day. So, what do we have to get stability there and to measure the new space? So we take an A square. And if you multiply A with A, it's like with the gnomon. So this is all time, and this is all space. So this is a time but dead, so it's not moving anymore in space. And this is time and vivid, but has no body. So this is space without time, and a time without a body, and this is a body which is dead. And the hyperbola is the new notion how to bring these things alive, to bring that into proportion. What is interesting here now, if I multiply A with A, so A by A to get A squared, this is always time, space. That's the important thing. So, and what we get is the diagonal. You know, if we have 1, 1, this is not a number at all, and therefore we symbolize it with a square root of 2, irrational. So that's here, and that's the area, the notion and the understanding of the area. Therefore, the area is a new space, a new notion of space. So that's a new day. So this is the last day, this is the last night, and this is a new day. This is of reality. We had it here. Past. This is what we call real. And this is the ratio. To cover, symbolize the irrational things with a new level of ratio. We can't describe this diagonal in terms of the old time, of the last night, and of the last day. It's a new day, and this needs a new ratio. So that's always like this. Now, go with the proof. How this is done. So what we first do is we move this point along this edge here, along the edge of B here. That's the first movement, which means now our triangle is this area, which is half of a square. We move it like here, and we know that this area here is of the same size like this, because it's a movement like this, space and time. So then we turn, second step, we turn it by 90 degrees, which means this goes here, this goes here, therefore we have this. And of course, by rotation, it keeps the same. So this area is the same like this area. We go with a parallel and move this point to this point. So this again moves, it keeps the area. It's again something like over time. So you go over time, you keep the location. So which means this area here is the same like this area. This is half of that, so the other half is this. So this is a square. Do the same with this is b squared. So these two give c squared. That's it. So we have 3 points. We want to make a constitution, a proper setup without knowing anything about the space, because it's a new space at a new day. We know the old space and the old time. We know that with the time we can preserve the space, we can preserve the area, and we take that to bring point A, point B, and point C into a constitution, into a constellation we can talk about. And that's geometry. To start to talk about a new space we don't know. This is what geometry is about. Yeah. So the hypothesis is, or this what happens is, this is 500 BC. Not this important. Then we go to the next step as 2 in the 14th AC, and we go to the next as 3 around 19 AC. The medium of the space so time is always coming with numbers. This is always with these symbols. So the time is coming with numbers, and space is always with new symbolization, with a new writing, not with a new calculation. So the mediality of this here, of this space here, are the rational numbers. So they establish they take the rational numbers, which is what is it called? T. So this is the scale of the new space. If you want to measure it, this is the scale of the new space, S1, established with these kind of constellations. In Renaissance, It's perspective drawing. I will go in detail how this works. I will give you understanding, a little more understanding, give you more volume to these arguments. That these, in today's terms, these are the real numbers. So these are series of polynomials of rational numbers and put them into proportion. This is the infinitesimal, the differential, and integral. But these kind of things you know, and they are somehow covered with the real number space. So this, I would say, is in a kind of simplification. I would say is a scale of the space in Renaissance. And what we have here is, today, it's a complex number space, which is what we see here with our diagram. We have the real numbers here. We say minus r with Gauss, and I here, the imaginary part, and minus I here. So, complex number space. So this is the scale of the space today. So to give more volume to these ideas, I want to show you how these perspective drawings are used in Renaissance to get a new understanding of space. Go to the computer. Go here. Interesting is that geometry is always about symbols. It's not about drawings. It's about hearing or talking space. And it's about the ears of the space. So, therefore, this code is, with this code, we enter and make constellations in the quantum or in the complex number space. The space of the complex numbers scale, whatever it means. So, this is the code. For example, we have a series of 5 numbers. We connect these numbers via a line. So this is our talk. This is a connectivity of 4 elements. We give these elements coordinates. So this is the topology. This is the topography. We create an infinite line, assign it as a screen. We get the coordinates of the viewpoint. We combine the connectivity, the topology, and the topography, and the topology, topology with as a graphic element. This is our writing, our talk, and to make it visible for the eyes of the time, we take a renderer, and it's called graphics. We get this graphics complex. This is a square. We qualify the screen. We qualify the viewpoint. And these are the parameters to the renderer, called graphics. If we evaluate that, we get these graphics: the viewpoint, the screen, and the graphical object. To do the actual perspective, it's quite simple. So this is the result. We have to get lines for each of the coordinates. This is for each, it's a mapping. For each of these coordinates, we create a line from the viewpoint to this coordinate. So we get 5 lines, and they are assigned to the symbol lines. So then we use the solver. We say for each of these lines, we want to solve, we find coordinates x and y, where is x and y is element of the screen, and x and y is element of the line. So for example, this one. And then we get this point. And for these are 5 lines. One is double. You get 5 points. One is double. Again, all this is for the ears of space. Now for the eyes of time. Again, we had all this with the lines. Now we qualify these points of perspective projection here, and then we draw the points. And this is the result. That's it. Perspective projection. So it's a kind of simple. So in doing it's very simple. Conceptually, it's a tricky thing. And you have to meditate. And I want to give you some hints how to do that. If you want to do it in 3D, it's exactly the same setup. This is a renderer. It's called Graphics 3D. We have the points, the viewpoint in 3D. We make these, we have these solvers. Now we solve with X, Y, and Z, but it's screen and the point, the view lines. And it's just the same. I'm a little lazy with writing all these coordinates for the cuboid. Would be long. Therefore, I put these macros. Took these macros, but that's it. So it's the same thing, and it delivers this setup, the viewpoint, the screen, the points on the screen with the lines on the screen, and the cuboid. So what we have is this. We are used to it on computer screen. So it's all these areas and so on, they move. But what we have is we keep the volume of this object stable in time. So I think this corresponds to the preservation of the area. So covering area. What we had here, to couple things, these are things, with these covering areas and with these kind of, with this Euclidean geometry, we decouple space from things. So with the perspective drawing, we decouple time from space. So we are able to talk about time, and space is encapsulated. Yeah. And today, whatever it means, I would suggest we decouple life from the scale of time. This is what I think we have in quantum space, which correlates to our interest in ecology, the green movement, environment, the health, and these kind of things. But which is in strong symmetry to what we experienced several times in our written history. So that, I think, is a qualification of the perspective projection. How to go from time to space. What happens at sunrise. So I think it's enough to trigger discussions. Thank you for watching, and see you in the next module.